Yeah. Thank you very much for this invitation. Actually, I registered as a usual participant in the parallel session for 10 minutes talk, but because I had to replace someone in the plenary talk, so I'm invited as a keynote speaker here. And unfortunately, I cannot practice my presentation about this. In fact, I prepared this presentation during the meeting. So I'm sorry that it will be not so good, but the title is The Hunting for the Nucleon Resonance. Of course, I will talk about what is the resonance, but before that, I will start with the construction, the units, because I am quite sure that here only a small part of the audience are particle physicists. I'm sure that everybody will complain, almost everybody will complain, what is the mass and what is the time in particle physics. So I will talk about the units first, and then I will go to the principle of resonance, quote unquote resonance. What is resonance here? And after that, I will talk about modeling the photo production. This is a process or reaction which I have studied almost 30 years. So you can imagine almost 30 years. And then I will talk about multiple models. This is a part of the photo production model. And I will talk about the second peak in the total cross-section. This is related to the choice of the resonance you need, whether it is D13 or D13. And finally, I will talk about the hunting for the narrow resonance. And as you can see here, there is no conclusion because I will leave it to the audience to conclude by themselves. The construction of the unit. Actually, this is the first part of the quantum relativistic lecture, because what are the natural units in this universe? They are nothing but the Planck constant divided by 2 pi and the speed of the light in vacuum. You know these values from the high school physics. But if we define these two fundamental constants to be one without dimension, this is very, very interesting and very, very, let's say, interesting, let's say that. Because if you have C equals 1 without dimension, you are free to multiply 1 kilogram with C squared. And remember that Einstein told us E equals mc squared, and you finally end up with 1 kilogram equals to 5.6 times 10 to 26 gigaelectron volt. This is a very small exercise. Of course, my colleague behind will complain. This is very, very easy exercise. Now, because C squared is also equals to 1, because this C squared equals to 1, finally we know that 1 kilogram is equals to 5.6 times to 10 to 26, 26 gigaelectron volt. Nothing is miracle here. And also, this is not so interesting because you know that the energy unit is equal to the mass unit due to Einstein's theory. But let's move to this constant. If I multiply each bar, remember that each bar is h divided by 2 pi times c. Because this is 1 and this is 1, the multiplication or the product must also equal to 1. You see that we have a definition of 3.163 times 10 to minus 26 joule meter equals to 1. That means I can write this equation or definition as 1 meter equals to this in the inverse of Joule, and then if you change it or replace it with electron volt, you will have this equation or this unit. That is 1 meter is equal to 5.07 times to 10 to minus 10 to 15 GeV fast. Now with the same reasoning, you can also calculate, this is exercise in the relativistic quantum mechanics, 1 second is also or can be expressed in GeV inverse. So this is very interesting because finally you don't need 1 kilogram, you don't need 1 meter, you don't need 1 second. You can say everything in GeV. This is really, really fantastic for me at least. And even the electron charge, you know the electron charge is minus 1.6 to times 10 to minus 19 coulombs is equals to minus 0.303 without dimension. This is also very interesting. Now, if you apply this to your life, because I always ask, what is the application of your research? This is the first application. This is obsolete kilometer per hour, and the future speedometer is C. This is 0.1 C, 0.2 C. C equals to speed of light. Of course, this is already dangerous speed. And you don't have kilometers here, you have light here. And if you have grandson, I'm sorry that you're still young here. I mean, in the future you will have grandson. If your grandson asks you, what is your age? You can answer 3.6 times 10 to 33 GeV inverse. In the future you have to figure this. And you can also measure your body weight in GeV. So you don't need kilogram here. GeV. I think in the future they will sell only GeV units. There is no more kilogram, hopefully. And finally, measuring distance. You know, this is Tucson, Green Valley. It's no longer in kilometers. This is 15 times 10 to 29 GeV inverse. But the most funny thing is, this is universal. So if there is or there were extraterrestrial intelligence, they will also claim they use the same unit. This is universal unit. So that's the first cause. The second cause, what is resonance? This is the principle of resonance. Yes, this is the same resonance. Take a tuning fork and hit it with a hammer. It will sound. It will give you a sound, and you see that only tuning fork with the same size, in the sense that it has the same frequency, will vibrate. This is really, I think this is a senior high school experiment, but this is still important. So the energy is transferred via the wave, and only the fork with the same frequency, we see that frequency equals to energy here, will resonate or will vibrate here, and the energy is absorbed by the resonating fork. So the energy will not be absorbed by this fork and by this fork, only by this fork which has the same frequency. This is the principle of resonance. Now, if you change the tuning fork here, this fork here with loudspeaker, for example, which can give or which can emit sound, and the frequency, you can scale the frequency, and from the lowest to the highest frequency, you will have this block. You start with a low frequency and you end up with high frequency, and the frequency which is the same frequency as our previous tuning fork here, the energy is strongly absorbed at this frequency. This is the principle of resonance. Energy is strongly absorbed at the resonating frequency. Now, what happens if we give energy to the atom? For example, this atom is the hydrogen atom. From Bohr theory, maybe you learn the Bohr atom from high school, if your high school is good enough, of course. The energy depends on the state, which is here expressed by n. N equals 1 is the ground state. The rest are excited states. So if you give energy to this hydrogen atom, you change the n. That means you change maybe in the Bohr way of thinking, you change the radius of this atom. But this is not really true according to quantum mechanics, but partly true. So something happens here. The radius maybe is disturbed, and the hydrogen atom is excited. We call it is excited to the excited state. This is also similar if you give this photon, or if you disturb a proton which contains of 2 U quarks and 1 D quark. They are glued by gluons. So something happens if you disturb this proton with photon, for example. You can also warm up the proton using an oven or something else, but using photon is easier. Now, the hydrogen atom and proton can be excited, as I previously said. This is the hydrogen atom. For example, you radiate the hydrogen atom with a photon. It will excite to an excited state, and this is the rule that the excited state does not have long lifetime. It will quickly go down by emitting a photon, because they have to conserve the energy. Energy must be conserved. So in this case, if your photon here in the beginning or in the initial state has the energy which fits this energy difference, it will excite the hydrogen atom, and the hydrogen atom excited the hydrogen atom will be de-excited or will go to the ground state by emitting a photon. The same also happens if you disturb a proton. The proton can go to excited state, but here, because the energy to excite a proton is high enough to produce a particle, the excited state will go to ground state by emitting a meson. Why not barium? Because it will violate the quantum number. Meson is okay. So for example here, if you excite a proton, it will go up to the so-called nucleon resonance, because proton belongs to the nucleon. It will go down to the proton state by emitting a ion. In this example is neutral ion. Now the good thing is that you can write down, or you can plot a cartoon if the time propagates in this direction from your left to your right. You can write this like this: proton is or proton absorbs the photon, it changes to the state, to the nuclear resonance, and it will decay to the proton and ion. In our community, we call it Feynman diagram. And the good thing also, Feynman did a good exercise. So you don't need to calculate too much. If you have the diagram, you have the rule how to write the amplitude or how to write the formula to calculate observables. Observables is something that you can observe or measure in an experiment. This is the plot of the spectrum of the hydrogen atom. Proton has also spectrum. In fact, it has spectra. It has the nuclear resonance spectrum. You can excite this ground state proton to the nuclear resonance here, depending on your energy, or you can also excite the proton to the delta resonance. You need more energy because delta has a spin 3 half, proton has spin 1 half. So to align the spin of the quark in the same direction, you need more energy. Now, this is the problem in our business because we have quark models from a long time ago. Quark models predicted many nuclear resonances. So, in fact, we have more nuclear resonances predicted than observed. The observed nuclear resonance is reported in the so-called particle data book. This is a holy book for particle physicists because they have the big one put in their room and they have small one put in the pocket. And every time they have time, they just print this small one. So this is a really holy book for physicists, particle physicists. So we have here missing resonance. In the sense that the missing resonance is the resonances predicted by quark models, but they are not yet observed by the particle data group, reported into the particle data group. Why? This is the question. Why this guy who published this book did not observe, or they claim they did not see this spectrum? Probably because they use only a pion channel. We call it pion channel. They use only the reaction which change the nuclear resonance to pi n channels. We have, for example, here pi n scattering, pi n to pi n, which can also excite the nuclear resonance. We can also excite nuclear resonance, which I showed you before by using photon. Using this reaction, this reaction. This is a pion-nuclear scattering, and this is a pion-nuclear photoproduction. Now, we claim that the particle data group did not use this channel. This is a very good news for me because I spent almost 30 years studying this channel. So, chaos hyperscattering or chaos photoproduction is my business. Maybe you can ask me why this is K lambda not Kn, because we have to conserve the strangeness quantum number. K has a strangeness +1, lambda is -1, if I'm not mistaken. This is the first indication. I'm really happy. This is really made in Indonesia because a long time ago, this is the first paper using the jurusan fisika at the time. And I'm also very happy that this is highly cited, almost 300, from 300 maybe 50 from my citation, self-citation. Now, let's go to the modeling of the chaos photoproduction. We have models which is already obsolete. It's already finished. Okay, I will finish in 3 minutes, hopefully. How to model this chaos photoproduction? As I told you before, use your imagination. First, use your imagination. Draw this diagram according to your imagination, and you can exclude the not permitted diagrams by using the concentration of quantum numbers. So if you have this diagram, you can calculate the this is an example. This is very horrible for you, for some of you, but this is very beautiful for some of us. How to calculate this is a famous rule. If you have this, you just put this. If you have the proton here, put this propagator, and if you have this guy, you just put Hawking constant. And multiply, you have the amplitude, and decompose it to this matrix. You have amplitude A, and from this amplitude A, you can calculate the cross section and other polarization observable, and you can compare it with data if you're lucky with more Nobel Prize. If you're lucky, of course. This is for example. This is a very easy example. Before 98, we have this data. This is very awful data because you can make model whatever you want at a time. We fit the model to the data and we have this model. This is using some nuclear resonances. In 98, unfortunately, or fortunately, I should say, we have more accurate data, which shows two peaks. The first peak here and the second peak here. The first peak is around 1.7 GeV. This is energy, but you can say it's also mass, because as I stated before, mass equals to energy in our natural units. The second peak, the model cannot predict unless we use the so-called D1C 1895. Using this nuclear resonance, we can really fit the data. At that time, I was very happy because I claimed it. How could I claim that we found missing resonance? Because the extractive properties of this resonance almost fit the prediction of the quark model. Only the sign is missing, but people in the quark theory say that it is okay to miss this sign because even in the quark theory they do not know too much about the sign. And this is we are very happy that they put it in the particle data book, although they say we do not use the following data because it is not so convincing. This is the collection of my collection of the particle data book. You see that nearly 1,500 pages and revised about 2 years. In fact, since they go or went online, they revise it every 1 year or even every 6 months. Now, the multiple model, I have not so much time to say about multiple model, but I think because my the next speaker is also high, so I can continue. I think this talk. For me, this is very interesting talk. I don't know for you. Remember that we have the model. Now we have so many n-star nuclear resonance. As I showed you before, we have spectra. We have spectrum. We have in fact maybe 40 or 60 nuclear resonances. And putting all nuclear resonances in a model is very awful because you have a lot of parameters, a lot of formulas, and even you don't know which one is this, which one is which. So why not use this simple formula? This is the so-called Breit-Wigner parameterization. So you can parameterize the nuclear resonances using this formula, and this is very simple. And my colleagues in Mart told me that they claim this has an advantage that the amplitude does not generate unnecessary additional background terms, as in the case of covariant calculation. Covariant calculation is our previous calculation using the Feynman diagrams. So we have added it. We use not so many, but you see here we use spin nuclear resonance with spin 9 half. 9 means 9 half. This is 7 half. 7 half. You know, then starting with spin 3 half. Almost all this is this. Let's say, I don't know what you call this, percentile. What is it in English? Say, what? Yeah, arguing or something like that. It's not correct. I mean, something like percentile. Let's forget it because this is international conference. So. And then we can write down the formula, and there was a problem because the experimentalists gave us 2 different versions of data. The first one This data, this is the so-called Sapir data produced in Bonn. This is made in Germany, and the second one is class. Our class data is made in USR. So they do not, or they did not agree with each other. The problem is that when I pick just the class data, I will end up with this blue curve. When I pick the Sapir data, I will have this red curve. If I pick the whole data together, I will get the so-called democratic solution, which does not produce any data at all. So this is really democratic. Doesn't produce class and Sapir. It was a big problem, and I think until now this is unsolved homework. And then to the second tick in the cross section, from time to time I heard about complaints from my colleagues. They said 30 marks confused. It was not D13. They said it's not D13. And in 2012, yes, 2012, when we went back from Osaka, from Tohoku, from winter school, we calculated the model, and then really we found that this was not the D13. You see here, we proposed two models. In the model A, we fixed the D13 mass with 1900 MeV mass. In the model B, we fixed the D13 mass to about 2 eV. So we fit this the data, and we have a better model if we fix the D13. And in all models, the D13 produce the second thing. So I admitted at the time, in the paper, I admitted that we did a mistake, but it was not my mistake. It was the data's mistake. So I clicked that. So we put it, and we are really happy that people from the particle data book replace or remove our data, our particle to this part, no longer in D13 but in D13, and we publish the result. And the narrow resonance, let me go to the narrow resonance because it's already time is over. Let me start with the pentaquark. What is pentaquark? Pentaquark is a particle contains 5 quarks. Not usually, I mean, in the universe, the particle contains 3 quarks or 2 quarks. 3 quarks called baryon, 2 quarks called meson. And there was no, at the time, there was no pentaquark. Diakonov et al. Predicted this pentaquark, and it was observed, quote unquote, observed by Nakano et al. in Japan. They found it in 2003. It was a really excitement at the time. Everybody talked about pentaquark, and I quickly calculated also the pentaquark production. Why is it so easy for me to calculate pentaquark production? Because the diagram looks like the same, like a chaos photo production, you know. Just change the coupling constant. Predict the cross section. Unfortunately, it was very small, so it was difficult to produce pentaquark. And I would like just to show you this history of the pentaquark. As soon as Nakano et al. Published their observation of the pentaquark, the status of pentaquark is 3 stars. 3 stars means the existence is from very likely to certain. So this is a really certain particle. 1 year after that, they reduce the star, 2 stars. Evidence is only 12. 2005, 2 years after the finding, the existence is very poor. 2006, 3 years after that, evidence is questioned. And 2008, really 5 years after that, this belongs to the history of science. You can read here. I'm sorry, I will read it because maybe you cannot read it. It's too small. This is the physics news in 2003. published by the American Institute of Physics. We will also publish our proceeding in the American Institute of Physics proceeding. Yeah? It was a false alarm. False. It's wrong. The whole story, the discovery, the tidal wave of papers by theorists and phenomenologists. Why this false tidal? Because I counted this. I think there were more than 1,000 papers discussing about this pentaquark in 5 years. So the tidal wave of papers by theorists and phenomenologists also belong to me. That followed, and the eventual undiscovery of this pentaquark is a curious episode in the history of science. This is reported by Particle Book again. Yeah. So pentaquark has died. It's dead. But how about its family? Because if it is dead, then we cannot produce paper. The rector will ask him, why you are not so productive? Because the pentaquark is dead. Okay, let's move to its family. The pentaquark has nuclear resonance and 1710. Diakonos also predict that it has sizable decay width to the Keelan lambda. This is again my business. So why didn't you calculate it? I was asked by my colleagues from Washington DC. So after the conference, I calculated and I can produce what he asked me in about 3 months and publish it quickly. This is also the same. The idea is just put a zero resonance here and scan the mass and weight and find the lowest chi-square. I found it. I said 1650. Wow, that's very interesting. We can publish it in Israeli, yeah, 2011. And in fact, I added one more paper about this. But again, this is deleted. They delete this particle after its lifetime only about 2 or 3 years. I'm really happy at the time, about 3 years ago, I was really happy that they put my name here. See, Mart. But this is rest in peace. Well, with this last slide, I would like to end my talk. I thank you very much.
Thank you very much, Professor Mart. It was a nice presentation. And the next part is questions from the audience. Any questions from the audience? Please. Okay.
I'm just curious if you just include the chaos channel with the lambda, because you said conserve the strangeness. What is your motivation behind that? Because you know that strangeness is not always conserved, especially in the big interaction.
Yep. Sorry. This is technology. This is not science.
Okay, thank you very much, Julio. Because, you know, we are using strong interaction here. And this strong interaction is dominant, not the weak interaction. In the strong interaction, of course, people will say it's wrong to not conserve the strangeness. But if you have a weak decay, of course, you can violate the strangeness quantum number. So this is our motivation. Of course, the model is not perfect in the sense that it should also include other coupled channels, coupled to pion, coupled to eta, and so on and so forth. But again, use the minimum effort, but still accepted by the community. What is right, what is wrong is here. You are right when nobody complains. You are wrong when anybody complains. So until now, I think nobody complains. So I'm right.
Okay. Any other question?
I'm curious if somebody understood my talk.